Spherical geometric construction. In this section, I'll show you how to draw the spherical platonics on the surface of a sphere. In Euclidean geometry, it is quite simple to draw a hexagon inscribed in a circle, and you start by drawing the circle and then use a compass to divide it into 6 equal arc segments, which define the 6 vertices of a hexagon as seen here. If you try to do this on the surface of a sphere, you won't get the same results. And this is where spherical geometry gets very interesting. When you draw a circle on a sphere, you actually define a cone. And I'll be referring to circles drawn on a sphere as a conics. The conics has a planar radius, labeled here as RP, that defines the base circle of the cone. The conical radius, labeled here RTA, is the side length of the cone, and is the length setting of the compass used to draw the conics. The length of the conical radius determines whether the conics will be drawn in the northern or southern hemispheres of the sphere. If you use a conical radius equal to the same radius as the sphere, it won't divide the conics into exactly 6 arc segments, as you would see for a circle on a plane. It divides a conics into 5 arc segments plus a fraction of an arc segment. But with some trial and error, a slightly larger conical radius will divide the conics into exactly 5 arc segments and define the 5 vertices of a pentagon seen here. Let me demonstrate. So we start with a blank sphere, and I start by drawing the first conics on the sphere. Then I place the compass on the conics and start marking off equal arc segments. When a conical radius is set correctly, it will define the 5 vertices of a pentagon inscribed in the conics. Now, referring back to the hexagon inscribed in a circle on a plane, one can draw 6 additional circles at the vertices of the hexagon and create a 6-petal design referred to as the flower of life pattern. Let me demonstrate what this would look like on the surface of a sphere. Now let's proceed to add 5 more conics centered at each of the vertices of the pentagon. And you'll see you'll start to create a 5-petal pattern on the sphere, which is similar to the 6-petal design we saw earlier on the flower of life pattern. This creates a 5-petal design on a sphere. Referring back to the flower of life pattern on a plane, you can also see that additional circles can be added at every intersection point between each new circle added, and this pattern would repeat itself indefinitely. So let's see what happens when you try this on the surface of a sphere. The 5 additional conics we just added has created 5 new intersection points on the sphere. We will now center 5 new conics at these intersection points, and these 5 new conics create 1 additional intersection point on the bottom of the sphere, where we will center the 12th and final conics to complete the pattern. And this will be referred to as a 5th harmonic. After drawing 12 conics, the pattern closed in on itself and became a seamless overlapping pattern where the conics intersect at the vertices of an icosahedron. Now we can draw the edges of the spherical icosahedron using a geodesic edge, which is equivalent to a straight edge on a plane. I'll demonstrate drawing the edges for one of the faces of the icosahedron. Here I'm using a geodesic edge to connect adjacent vertices of the icosahedron to define one of its triangular faces. The face axes of the icosahedron can be found by triangulating from the vertices. And let me demonstrate that. The 20 face axes of the icosahedron are located by using 3 arc markings from each of the vertices of the icosahedron, as seen here. The face axes of the icosahedron also correspond to the vertices of the dodecahedron and will allow us to draw the pentagonal faces of the dodecahedron. Let me demonstrate that. After locating the 20 faces, which are also the 20 vertices of the dodecahedron, we can proceed to use a geodesic edge to start drawing the 30 edges that will define the 12 pentagonal faces of the spherical dodecahedron. And the edge axes of the icosahedron and the dodecahedron are located at the intersection point between both of their edges, which can be seen as perpendicular to each other. Let me demonstrate. The edge axes of the icosahedron and dodecahedron are perpendicular to each other. Now let's move on to the next harmonic. Next, we will increase the length of the conical radius until we can draw a convex and use its radius to divide it into 4 equal arc segments. Let me demonstrate. For this next harmonic, we are looking for a conical radius length that can draw a convex and then be used to divide itself into 4 equal arc segments and define the 4 vertices of an inscribed square in the convex. Now this does take some trial and error, but when you find the correct length for the conical radius, it will define an equator or great circle on the sphere. The conical radius can then mark off 4 vertices of a square inscribed in the convex. We can now move the compass to the 4 vertices to draw the additional convex, and let me demonstrate. Now let's proceed to draw additional convex at the 4 vertices of the inscribed square in this convex. This creates 6 intersection points on the sphere as seen here. While it only appears that there are 3 conics on the sphere, there are actually 3 pairs of conics. Each pair of conics are centered at antipodal points on the sphere and overlap each other. The intersection points of these conics define the 6 vertices of a spherical octahedron. We can also locate the face axes of the spherical octahedron by triangulating from its vertices. These face axes also coincide with the vertices of a spherical cube and allow us to draw the edges of the spherical cube. Let me demonstrate. The 8 faces of the spherical octahedron, which are also the 8 vertices of the cube, can be located by using 3 arc markings from each of the vertices of the octahedron. After locating the 8 vertices of the spherical cube, its 12 edges can be drawn with a geodesic edge, and this is known as a 4th harmonic. Now let's move on to find the 3rd harmonic. We will increase the length of the conical radius until we can draw a convex and use its radius to divide its circumference into 3 equal arc segments and define an equilateral triangle inscribed in the convex. Notice that the convex is drawn in the southern hemisphere of the sphere, making it difficult to construct. This does require a spherical compass to construct. Let me demonstrate. For this new harmonic, we are looking for a conical radius that can draw a convex and then be used to divide itself into 3 equal arc segments and define the 3 vertices of an inscribed triangle in this convex. Now we can move the compass to the vertices of the inscribed triangle and draw the additional convex. Let me demonstrate. Now we'll proceed to draw additional convex at the 3 vertices of the inscribed triangle in the convex. This creates 4 intersection points on the sphere that define the vertices of a spherical tetrahedron. Now we can see that the 4 conics intersect and define the 4 vertices of a spherical tetrahedron. Now we can proceed to draw the edges of the spherical tetrahedron and locate its edges as well. Let me demonstrate. Let's use the geodesic edge to draw the 6 edges of the spherical tetrahedron. We can also identify the center of these edges of the tetrahedron as a midpoint between adjacent vertices of the spherical tetrahedron. And in a similar fashion, we can identify the 4 face axes of the spherical tetrahedron. That's seen here as well. This is known as the third harmonic. In our next video, we will derive the exact values for the conical radius for all of these harmonics.